Okay, now once we introduce orthogonality, but in order to introduce product, we need to have some kind of sign measure of orthogonality. And there is a very long discussion in the preprint that shows that it can be defined intrinsically, so only from the topology and relative orientations, but it's too complex, so I will do for the simple case. So definition. Let K be a quasi-cubical mesh K with convex embedding in manifold K such that the interior. So this is convex, so convex, and this is just a reminder. This is non-convex because, and I think I made some mistake here. Yeah, such that so I say slight mistake, but the idea is that orientation of A should be, and let me give example. 0, this is A1, and this is F. Should be a form on this direction. So this is X direction, so I will call orientation of E0 to be dx. Orientation of E1, B, C, and F0. Then orientation of B, which the orientation with Y is minus. So we have that orientation of A is minus orientation of A with orientation of B with C. Therefore, epsilon perpendicular of ABC is -1. So this is dx wedge dy is minus dx wedge minus dy. Written properly. Or it can be even some positive function. F should be the reciprocal 1 over F. Now let's give a trivial example. I have something here. So I will call this I don't know what is the right orientation, but B, this will be C, and the whole volume will be A. So orientation is dx wedge dy. Okay, so what is the sign here? dz times dx dy, what is the sign? Is it plus or minus orientation of A? It's plus because it has two changes to be made. two swaps. So this is example inside the definition. Let me finish the definition. Okay, let me be a separate definition. Okay, let's some note. Relative orthogonal orientations only terms of relative orientations, which is the boundary operator, relative operations, and the mesh topology. But I'm not going to do that, obviously. It's a very long discussion in the preprint, so. Oh, yeah. Epsilon, so these are epsilon, and the mesh, which is this here, the boundary relations. Something to be a subset of another. And now we can define the cup product. It satisfies all the conditions I gave before. So let K be a quasi-cubical mesh. The cup product on K is defined by as follows. So if sigma is a P-form, a P-chord chain, rho is a Q-chord chain, and A is a P plus Q cell, then smile rho of A is the sum. So these are the coefficients. The relative orientations will be the coefficient. This will be the sum of BC that are perpendicular. So previously I said that it should only depend on the boundary, and here only depend on pairs of topologically orthogonal cells. And now we have epsilon perpendicular A, B, C times sigma A times rho sigma B rho C. Or everything divided by 2P plus Q. This term is, so this can be put here. The coefficient is the plus minus 1 over 2 to the power of P plus Q. And we have a theorem that the above operation satisfies the coproduct axioms. Okay. Now let's give example. I'll do only in 2D because in 3D, if I have a cube, it will have a lot of terms and at least many terms because it has 6 faces and 12 edges, and there'll be a lot. So I'll do only 2D. And 0 and 1 and 2 and 3, E0, E1, E2, E3, and F0. Okay. Now, let's start with 0, 0 is very trivial, but P equals Q equals 0. Then sigma rho at N0, for example, is sigma N0 times rho N0. Sigma will be in Cp of K and rho will be in Cq of K. So this is for 0. Now if P is 0 and Q is 1, sigma rho, let's say at E0. So this will be 1/2. This will be, okay, 1/2 of 0 plus 1. And then epsilon perpendicular of E0. And then I'll have two terms. N0, E0. Times sigma N0 times rho E0 plus sigma N0 times rho E0. One of the terms is 0, so the perpendicular is always 1. So the whole result will be 1/2 of sigma of N0 plus sigma of N1 times rho of E0. And that's why we have half, because we have two terms. E0 plus the average of these things. For this, will be rho applied to this with average of this. I did only for one cell, but for a single edge, but for edges is similar. This will be similar. All the perpendiculars will be 1, and this will be 1/4 of sigma N0 plus sigma N1 plus sigma N2 plus sigma N3 times a rho of F0. Yes. So when we apply, when one of the dimensions is 0, it's the non-zero cochain applying at this cell multiplied by the average over the bound of the nodes. Now the most interesting case in this in 2 dimensions is when both are 1, P and Q are 1, and then sigma rho of F. So this will be again a 2. P plus Q is 2. So this will be 1/4 again, 1/2 to the 1 plus 1. We have E0, E2, E0, E3, E1, E2, E1, E3, but then we have in the opposite directions. Something is off. Maybe this is normal. I'm not sure. So this will be 0 times rho of E2. Plus, I'll have a lot of terms, all of them, but the end result should be 1/4, and then, for example, this will be E0 with E2. This is dx, this is dy, so the whole result will be +1. So this will be sigma E0 rho E2. But we will have the opposite, so it will be with the opposite sign. We'll have this with this. E1 rho E2 plus E1 rho E3. But then I will have minuses in the opposite direction. So sigma E2 rho E2 rho E1 minus okay. Now let's start with the metric part. So now continue with Riemannian meshes. So far we have and such that and mu from M to R plus gives measures to all cells. Zero cell is dimensionless. One cell is per meter, and so on. I will not write everything. And we say that M with mu is a Riemannian mesh. M is embedded in a manifold X with embedding phi. So phi is function from M to subset of X. Then usually in the embedding so for instance, if I have this thing here, a circle, some diagon, let's get this example. Maybe this will be 1/4, 0 and 1. This will be E1 and this will be E2, F0, and this distance is R. So this is R. And we will have the measure of N0 is the measure of N1 is 1. The measure of E1 is P over 2 times R. Measure of E2 is 3P over 2. So this is 1/4 and this is 3/4. The whole is 2 pi R. And the measure of F0 is PR squared. Okay. This was some example. Now, when in the smooth exterior calculus, we had metric tensor, inner product, Hodge star, codifferential. Now, initially in the 2022 paper, I introduced some metric tensor, but later I did not like it and introduced direct inner product. But if you introduce the inner product, the Hodge star and the codifferential, the Adjoint Coboundary code, come naturally. Now for the metric, I decided, because it would be easier computations, to be diagonal. So two adjacent cells will have 0. So start with a Riemannian mesh, M mu, be a Riemannian mesh. Products. So it's a function of two arguments, P from CPM times CPM to R. In the smooth case, that was function from omega PM times omega PM to R. For P for 0 to D, so this is the dimension of M, of course. So that basis cochains, and so that means that the bullet, the basis element, a bullet 0 when A doesn't equal to B, and for C in a P cell is, now let's give examples. Let's do a single square. This is example. So here, I didn't, B perpendicular C means that there exists, oh, this is the wrong definition. Yeah, this is so, sorry. So, somewhere A is a D cell and BC is perpendicular to A. Yeah, this is the right definition. The previous was kind of true when it's not convex, but if it, in this case, here perpendicular to with in P in such that BC are perpendicular to A. No, the opposite. Okay, now let's compute the Hodge star at a 0 cell. So let's start with P equals 0. Sigma is 0 cell. And we compute star 0 as sigma. Now it has to be applied at a 2 cell. So it should be applied, for example, at F0. And this should be 1 over F0. Sorry, 2 to the power of 2. And then I will need the perpendiculars with orientations. This will be only sigma n0 plus sigma n1 plus sigma n2 plus sigma n3. And this was 1 over this, so this will be f mu of f0 divided by 4, and then sigma n0 to sigma n3. This is how you compute it for 0. Sigma star 1 of sigma, so P is 0, sigma is 1 cochain. If we can apply it, and then we have to use orientations. Here, I don't know the signs, so I'll just keep it that way. So I don't know the signs, so I'll just keep it that way. So I have epsilon perpendicular F. So this perpendicular with this is in F1. So F1 E4 0 times sigma of E4 plus E perpendicular F1 E2 is 0, sigma of sorry, this is F3, not F1, F3. And finally, let's do 2 form. So P is 2, sigma is in C2. And apply it F at, and this will be 1/4 of N0, which is computed from before. And then I have the values over the surrounding faces. So this will be sigma E F0 plus sigma F1 plus sigma F2 plus sigma F3. So Hodge gives some averages with when and summing the perpendicular stuff. So it gives some kind of, if I start here, it gives a linear combination of the perpendiculars, like sigma of dx of sigma of dy is some like these are dx's. Okay, and I want to finish with the codifferential, adjoint coboundary, because it's not good to leave it for the next time. Be compatibly oriented. It's not necessary to be. It's just anyway. I'm not sure why I did that. Yes. I not need compatible orientation. I don't know. It'd be a Riemannian mesh. The adjoint coboundary operators. So these are delta P star from C P K to C P plus 1 K. These are with zeros. P is from 0 to D minus 1. Of course, this is the dimension of K. And CP0 are 0 on the boundaries. Have 0 trace. Yes. So they're zero. They're only defined for cochains that are 0 on the boundary. This was the same in the smooth case, so that can be not 0. And if you want to compute them on the boundary, it's not a good idea. And then are the adjoint. This is P plus 1, sorry. Are the adjoints of dP, i.e. for any sigma in P plus 1, eta in C 0 on the boundary. Delta P plus 1 star sigma with eta. This is the P dot inner product is equal to sigma delta P of eta. This is P plus 1. And so we have the following theorem. Of course, in the above notation. Delta if B is in the interior is in the interior of K minus 1, and sigma down this time is 0 on. Then delta P star sigma at this cell, A bullet times C bullet. It's like the boundary operator, but with some coefficient. Why? Okay. If there is something wrong, I'll fix it. Okay, so in this case, we have B1 and B2, delta 1 star and delta 2 star. So E equals 1, delta 1 sigma at, let's say, at N0. So this is 1 over N0. And then I have all the cells around it. So E0, E3, maybe have to put E5 here. I have epsilon E0 N0 times E0 E0 sigma at E0 plus epsilon E1, E3, E4, and E5. E3 plus epsilon E4 and 0 plus epsilon E5.
I have a question.
Yes?
B is a cell.
Hmm?
B is a cell.
Yes.
What are the big dots?
The basis chains and cochains. Okay, so B dot basis chain and B superscript a basis cochain. So this is like here, this is should be like NI, and this should be